Okay, thanks. And it's really my pleasure to be here today to talk about our recent work on building certifiably safe and correct large-scale autonomous system. I have a subtitle here because this is really what we are doing using machine learning to solve some challenging safe automatic control and planning problems. And I made a pretty wise choice not to have a motivating slides because I know my previous speakers will be able to give a pretty good introduction on why we want to use machine learning to solve control problems, why control problems are essential. Control theory is essentially there to help us make our system more safe and stable. I'm not going to repeat anything of because I know they have done a very fantastic job. Now, what I'm showing here is one of the simulation environments that we.
Sharing. You do share actually, right? Okay.
Am I sharing?
Should be sharing, right?
I think so.
Stop sharing. Yeah, it should be.
Yeah. And this is one of the simulation environments we're trying to build, kind of giving you a vision of what I mean by large-scale autonomous systems. We're working on drones, not really actual drones because we put thousands of them in the city. It will be hard and very expensive to run all of them in a city. It's a kind of a city environment in the game engine. Now imagine that you're going to play a game either as a person or a artificial intelligent player that play all these drones, move them to their desired location, make sure they never collide, they never get swapped to a wall because of wind, they never run out of battery. So those are the safety challenges here we want to solve. Now, if I want you to do that or any machine learning algorithm to do that, then there will be a bunch of challenges. The first things that came to my mind, and that will be exactly the problems I will talk about here today, is the following. First of all, we have many of those challenges, many of those agents. Now, probably I feel good about working on this problem and publishing by saying, actually, we cannot do it hardware, just too many of them. We will stay within simulation. High dimensional space, in a sense,
I'm sorry, your screen is not shared somehow, even though it says it's sharing actually. Have you encountered this problem? Maybe it's a problem of the adapter before?
I don't. Maybe let me try again. Share screen. And what I did was this one. Are you able to see it?
Yeah. Sorry.
No problem. Yeah.
No, it's still black.
Oh, interesting. Sorry about that. Let's try to figure out this technical issue. Maybe let me do, I don't know whether, is it a network issue?
It should not be. I mean, have you encountered something like that?
No, I've never seen that before. Let me see whether it helps if I measure my screen. Oh.
Yeah, it's still black.
Actually, I have stopped sharing.
No, yeah, sorry. If you share again.
But I have stopped sharing. So,
and if you share now again? Still black. Okay.
It shows I have started screen sharing
exactly.
here, but
Yeah.
somehow it's black here. That's weird. Let me see.
Which network are you on?
I'm on EDU ROM. Is that an issue?
No, it's not.
Yeah. Yeah.
Are you showing the screen or the PowerPoint?
I'm sharing the PowerPoint.
Try showing the screen. Check the monitor.
Okay. I don't see a second.
Just the desktop like that. Share that.
Okay.
Yeah, now we see.
Now we see, but when I play this, which one?
Yeah, looks good.
Oh,
I think that's good. Yeah.
Interesting.
No, yeah.
I'm seeing a different screen here, but it's sharing that screen.
Thank you very much.
Okay.
So sorry.
You can
Sorry
drag-
about-
You can drag that over to your screen. If you don't want to see that there.
Yeah.
Drag from the bottom from where it says your screen, the green part.
This one?
Yeah. Drag it over.
I can drag it. I can also hide it
First
here.
click there.
This
yeah,
one.
that'll-
All right. Sorry about that interruption. So okay, let me continue from here. The challenges we're interested in solving here. A lot of agents, high dimensional space. This high dimensional could be from a lot of different resources. We could have a dynamical system that has a super high dimensional state space. We could have a high dimensional input space because you want to use, for example, LiDAR or camera as your input. And it could have a high dimensional uncertainty space. And a related question here is when, especially when the system becomes high dimensional, the modeling now becomes a little bit tricky. We sometimes have unknown model or the model becomes imprecise. We may be like, if we learn on an imprecise model, what that indicate. And finally, I'm also very interested in complex requirements because it's easy to encode like collision avoidance and these things, like pretty naive safety requirements in the learning process. What if I say the task for these drones, for example, a couple of them should have to accomplish a task altogether, and there are these charging stations deployed in the city. How would I distribute the charging stations? How would I fly the drones so they can get charged when they need to in a smart way? And in today's talk, I'm going to mainly kind of talk about how the further three challenges can be solved using this idea of combining neural network and machine learning with control theory. And I will mention a little bit about the complex requirement part if I have time. So when we talk about large-scale autonomous system control, there are definitely a lot of approaches that have been developed, all the way from traditional control based on optimal control, optimization-based approaches. They're not necessarily different. Optimization is a way of solving control problems. And all the way to nowadays reinforcement learning. I put constraint reinforcement learning because safety is one of our major concern. We want safety to, being safe is one of the constraints. Now, when we use control-based approaches, we usually have a higher assurance level in the sense that by applying control theory, we find a solution. We can trust this solution in a whatever way, like a robust way. If we have a Lyapunov function or optimal-based control, we know they are robust to some extent. And we can trust what these results can let us drive the system, what the system is going to be like. And versus reinforcement learning, it can usually, people have proved that it has a pretty good scalability. It can scale to quite large scale systems. But you can see like we are often kind of facing a trade-off between the assurance level and the reinforcement learning using these approaches. And by the way, a disclaimer, this is not an exclusive list of all the approaches. And this also does not represent all the development or the recent, especially the recent development of these approaches. There are approaches that can improve safety while maintaining scalability. There are optimal control-based approach that can do better in terms of scalability. So I'm just saying in general, this what the field looks like. Now, what we are working on is called the neural certificate-based control. And our hope, and I hope that I can convince you by using neural certificate-based control, we can sort of break this tie and push good assurance level and scalability. And the secret is really like, how would we bring the strength of the rigor in control theory and the effectiveness in machine learning? When I say neural certificate, I really mean the certificate functions. The first line of certificate functions we can get is from control theory. And I'm listing a few of them here. Lyapunov function, we have heard how they are being, how to construct them, how they look like, how to use them to assure stability. Barrier function, instead of a Lyapunov, barrier function is very similar to a Lyapunov function, but instead of converging to an equilibrium, you kind of enlarge that equivalent to a set, and you want your systems to stay within a set. If you're outside, you want it to come back within a safety set. And that can certify an invariance. Invariance means something that doesn't change. If safety is an invariant, then we have the certificate for safety. And contraction metric, we have also heard a lot about contraction metric today from Professor Slotting. Basically, he's the inventor behind this. I just told Professor Slotting my whole career is built on contraction theory. You heard that I won the dissertation award from ACM. What I really did was to use contraction theory to do verification, and they like it. And my first line of work when I started my faculty 2 years ago was to learn a contraction metric. So pretty much like my career is based on contraction metric. And I know Professor Slotting is here. I decided not to talk too much about contraction metric because I know he's going to give you a very good overview of contraction metric. But they pretty much work very similar. Let me use barrier function to tell you this process of using neural networks to encode them and how to find them. It's actually, after I talk about that, hopefully you can see it's a very intuitive, very straightforward approach. Now, I listed the condition for the barrier function. Here it's a scalar function, very similar to Lipschitz function, very similar to the Lyapunov function, with almost the same conditions, except for the last one. They're almost similar. We want the value of this function h, which is the barrier function, to be smaller or equal to 0 when the states are safe. It's bigger than 0 when states is unsafe. Now, these two, why it's called a barrier function? It's because h equals 0 is a barrier that defines from, like, tell you safe from unsafe. Now, from here, h is really just any classifier that you can find that can tell you which state is safe, which is unsafe. And the last one is saying the derivative, the time derivative of h should be smaller or equal to 0, but there's an extra term here. There's the alpha function. Alpha function is a class K function. What that is doing is really telling you within the safe set, you don't have to always converge to the equilibrium. You can kind of work around, but when you are getting too close to the boundary, you should turn around. So that is what this function is trying to say. But other than that, it's like a generalized Lyapunov theory. And the way to prove it is also through a very similar proof through Lyapunov theory. Now, we have seen how H looks like. In control theory, there are many approaches we can use to handcraft an H function based on your safety criteria. This is particularly has been studied by a lot of people for like relatively easy dynamics, linear dynamics with like a collision avoidance kind of constraints. We know all the conditions for H. Unfortunately, it's still pretty difficult to construct that H if your system has a super high dimensional dynamics, and like if your control input is not directly affecting your dynamics, but it has to be integrated multiple times, the higher like orders of the control input can affect your control system, like those under-actuated systems. For nonlinear dynamics, in general, they are pretty difficult to find. And for safety constraints that are non-convex, all these things make finding H a pretty challenging problem. But it's no longer that challenging if we use neural networks to represent that H. So there's a line of work by researchers from UCSD back in 2019, so the New Rips paper called Neural Lyapunov Control. What they said in the paper was basically we can use neural networks to encode both this barrier function and this controller input U. Now you may wonder where this U, why is U? Because you also changed the third condition here. So we have to have some sort of control policy. And now if we have those two, we just need some sort of loss term to guide us find the correct weights for the neural network. And this loss term is super straightforward. I have put it here. It's basically encoding the three conditions here by penalizing the violations. So I have color coded the same one, like the green one is encoding the first condition. It says, I want H to be always non-positive when the states are safe. If it does, then I will penalize it. Like the rest of three are basically the same as the previous. So very straightforward way of doing that. And let me just do a very quick recap of what this means. We use two neural networks. And some people may often ask me, can we use one? Yes, you can use one, any architecture that you want to use, as long as you have one output for the barrier function, one output for the control policy. It doesn't matter. And we use this, we sample. There are different ways of doing a sample. For lower dimensional systems, you can directly sample in the state space. For high dimensional systems, you can sample in the trajectory space. And with a little bit trick that I'm not going to talk here, but if you are interested in that, I will tell you the details there. Then we have this single lost term I have shown here to backpropagation to find the weights. That's how it works. And now let's see like what it will look like. I have shown two cases. The first one is a LiDAR-based robot navigation, where the robot will have, it's actually a drone that have to go to this dark region while avoiding all these pink obstacles. And the right-hand side here is a satellite in the middle, and another satellite is trying to orbit around it. Now, for this one, it's pretty clear we want to collide with the obstacles. You can see that this barrier that we have learned sort of align pretty well with the outline of the obstacles. There are some violation here, but another condition saying I have to go to the darker and darker region. So it will actually, wherever it starts here, it will fly to this darker region. And the right-hand side here, it's saying the orbiting satellite should not fly too far away, meaning it's outside this purple circle. And it should not get too close to the inner one to avoid the collision. So it should not get into this inner purple circle here. So basically stay within the ring defined by the two purple region. And it's clearly a non-convex safety constraint here. And ultimately we want the satellite to be able to converge to within these two green regions. This blue one here is define the barrier we have learned. In both these two cases, they are pretty small neural networks with 2 or 3 hidden layers, like 64 neurons each layer. So they are not big. Basically, we are able to learn a barrier like this in both the two cases. Now, does that solve all the problems? I would say no. It's especially when I'm saying we work on large scale autonomous systems. Of course, this one is not large scale, just a toy example to show you what's the problem here. So here, the 4 Dubin cars, like a very simplest nonlinear dynamical system you use to describe the car we're driving, they're tracking their own path without a collision avoidance controller. I just want to show you that their color will turn if they're getting too close. So there is a violation of the safety constraint here. And there are multiple ways of adding a safety controller on top of it. One way to do it is follow what I just said. We learn a barrier function because it's neural network. We can just learn a barrier function for like a large system. We put the four states of those 4 agents into a big vector and learn a barrier function. Does it work? It works. You can also try to penalize the case when they are colliding. It also works. But is this a good strategy to solve for such problems? I would say maybe not, because first of all, this centralized way of penalizing collision is not scalable. If I'm able to find a collision avoidance controller for like 4 agents, or I find a barrier function for collision avoidance for 4 agents, what if I want to run 4,000 agents, like in the case I have shown in the simulation? I probably have to redo it, retrain it. And with 4,000 agents, that would be a nightmare. Like each of these agents, if it has 10 dimensions, now your input dimension is like 40,000. That's not a very scalable way. So instead of using this centralized approach, one good thing about all these certificates, including barrier certificate, is that it can be decentralized. The Lyapunov function can be decentralized. There's a whole theorem about input state Lyapunov theory and how to use it to construct a global Lyapunov function for network system here. For barrier function, we figure that it's actually also pretty easy to decentralize a barrier function. So what we did is we decentralized the barrier function together with a decentralized controller. And if I tell you, if I just like write down how the decentralized barrier function looks, it's actually almost the same as what you have seen, right? Yeah, the 3 conditions here are almost the identical copy from the original definition of the barrier function. But the only difference here, now instead of defining my barrier function over the entire state, I define it over its own state and the observation. what you mean, I mean by observation, it could be anything that you see, like could be some sort of perception system that tell you what's around, or it could be as easy as local observation that is given by LiDAR. We directly take the ray, like the radar, like the arrays from LiDAR as our input, like the LiDAR array. And so that's the first thing we have done to just decentralize everything. And with doing that, actually, we do not lose the confidence for safety, because even if we do not have to learn for a global barrier function, we know it's there. In this case, we just take the maximum of all of them. That's a global barrier function. So you know there is safety proof for the global safety underlying there. We don't have to learn it in any case, in every case. And the second thing we are going to do is to handle this OI here, this input, like for example, it's a LiDAR measurement. What's the problem of just having an OI here? There are actually two issues here. First of all, this OI is changing, right? And if I use a local observation, that observation will always change. That point, like the LiDAR array point that reflected, if there's no obstacle, it won't give me anything. So I may have a changing amount of that. Or if I use like camera-based observer, there'll be like anywhere from 0 to a very large number of neighboring agents, dynamical agents there. So that number will change. In control theory, it may not be a very straightforward way to encode a changing input into our system. And the second problem is this: to be able to use a third condition, we have to predict OI, right? Basically, there's an OI dot here that we have to know, which means you know the derivative of OI. And we actually, how would we know that derivative if we don't have any information of the system? So those would be the two challenges we have to tackle. And luckily, it's not that difficult either to encode the time varying observation. What we did was just to use a permutation invariant embedding. This seems pretty common these days. I have seen many people doing this, but back to like 3 years ago, when we started to work on this, this embedding was not a very popular thing in robotics. Now it's becoming more and more popular. Basically, there's many different ways of embedding a changing input into a fixed length input. What we use was just the max pooling layer here. And you can now have seen people just embed a camera-based input using vision transformer or something to a fixed length input. I think that also works. But for us, it's just one single max pooling layer at the end of the neural network that can give us the fixed length vector. So that's the first step we have done to encode a time varying observation. Now, second step, we still have to deal with that OI dot. You pretty have to have some sort of understanding of how your input is going to change your observation. For a LiDAR-based system, this is actually a very, very smart idea by my student. Basically, for this LiDAR-based input, the control input, what it will change is the workspace translation and rotation for a ground robot or for an air robot. And that basically means some AFAN update to the LiDAR observation. If we have this model, then we can actually do the prediction and compute the O dot by searching over the different control input and how the AFAN transformation is going to be done based on different control input. And this is for LiDAR and works pretty well. I can show you some visualization result, but it doesn't really work for camera-based input. For camera-based input, what you need is a generative model here. We have some recent work trying to get a generative model for that O dot, but it's under review anyway. And I want to first show you how it looks like in this case. So if you still remember the toy example I showed, there are 4 cars trying to follow some sort of their own path. Now we train that decentralized barrier function together with a decentralized controller. The training environment, if you're interested to know how it looks like, is just an empty space with all these cars running around. Now within simulation, what's good is that you can allow them to collide and you can sort of collect some unsafe states in simulation. And the decentralized controller is basically the same controller that we just learn one copy of them because they have the same dynamics. This controller is going to be deployed on all the agents. So they each have a identical copy of that controller. Now you can see if we do that, then these agents they're able to nicely avoid each other, while they can still track their original path. Now, how to track their original path, you can learn contraction metric to do that, and you can have both. Now, to understand how these can generalize, we train on 8 agents because 4 is not enough to give us the variety of the observations. We decide to train with 8 agents. And the resulting controller, it's still just learn 1 copy of that controller. We're not learning like 8 copies of those. So it's 1 copy of the controller, 1 copy of the decentralized barrier certificate. And if I put them on those cars, they are all of the same dynamics. They all have the same controller now on top of their original controller to do certain things like formation or following path, or just go to their random location. We can see that they pretty much like avoid the collisions in a very nice way. And what we have observed here, if you see in the formation case, what it has implicitly learned is actually some sort of roundabout, right? Like that's actually amazing. They learn a roundabout in the middle to be able to go to their destination without being disturbed, like without getting stuck there or without colliding into each other. So the last case is more than 1,000 agents. They're trained using only 8 of them, but can scale to 1,000. And theoretically, as I said, 1,000 is not a limit. We don't have a limit. The limit is arbitrary, but there are limits. For example, all these simulation environments, if you look at the rough density, they are roughly the same. If you train, for example, in a very sparse environment with 8 agents and you put 1,000, it won't work because they haven't really collected enough observation data in the training. But they roughly like have the similar number density in the environment. We have also done this for a 3D case, all these drones. And it's basically using the same procedure. This is a relatively simple environment, and I will show you how it looks like in the actual simulator that I've shown in the first page. Now, you may wonder, what is decentralized barrier certificate? What is the thing that I have learned? I have plotted 2 cases here on the top, both ground robots on the top. You will show the actual environment later, but it's like a lot of those these containers and all these trucks will have to move around the containers to move things around, and they are all decentralized. They have their centralized controller in the sense they know where they're supposed to go next. But other than that, they have decentralized controller for collision avoidance. And this bottom case here is an actual roundabout with all the cars driving here. What we have observed is the learned barrier function is actually some sort of a sign distance function. It's very similar to that. But what's more than a sign distance function is that it actually can tell the policy to go to the further and further area of the like from the unsafe. And you kind of see that this, for example, it learned this kind of barrier at the white kind of curvature here. So now that's how it looks like. By the way, this is like the decentralized barrier function from an agent that's not here because it's supposed to join this corner, and how it view the scenario here locally if we can observe all these agents here. So before I give you some more visualization result, I want to say that this architecture I have described using a neural network to encode the certificate function, another neural network or another part of the neural network to encode the policy can really be used to learn any of these certificate function that I have mentioned. We actually started with contraction metric, and we realized we can learn barrier function, we can learn Lyapunov function, we can learn decentralized version of them. It's actually much more powerful than we thought when we started to use this. There are several things you can do after this training process. This proof we have learned, remember, they each actually give you a proof of the corresponding property like stability, safety, contraction, and you can also have a subset of those. You don't have to learn one certificate function at a time. You can have one neural network that include multiple certificate conditions and learn them all together to have multiple properties being certified. So that can verify some sort of a desired system property. This policy that we have learned can be used in closed loop with the system that you see how it performs. But even if they do not perform perfectly, this policy due to various reasons, because, for example, the model is not very accurate or the environment has changed, we can use the learned certificate function to further modify and monitor their policies to make sure they still satisfy the properties. So this is overall how it looks like. And if I compare this with constrained RL, everyone compare with RL because that's probably the only thing that we can make it work on thousands of agents. The first scenario we can see in here is like a corner of the city. Let's see, what if that 1,000 drone somehow decide to go to one corner of the city? And how would we, if we follow this guy here, this guy is the one we let it like move and see how the barrier function works. It has a LiDAR-based input that can tell you where are the neighbors. And if we can see here, follow it carefully, this is doing like collision avoidance pretty nicely, while the other reinforcement learning, like it's not like we fine-tuned them to perform bad. It's just like we have done whatever we could to make them work. I will show you some more quantitative results. We have also tried this on boats because boat is a kind of interesting thing. Boat has very big inertia. If you feel you're already colliding to some boat, it's already too late to turn. So that's why probably you can see the some RL boat, we feel like it intentionally try to collide with all the other boats. And if we see some quantitative results, this result here is average across all these simulation environments here. To air, they are the same thing, but this one is more sparse. This one is like we squeeze all the drones in the one corner of the city. We have boats, we have the ground vehicles, and average around over all these scenarios, each contain 1,024 agents. And this from this number, you can probably tell the student is from CS. Like they would never use like 1,000, they would use the power of 2 for whatever experience, the number they would like to choose. And so our result is up here. The x-axis here is the relative safety rate. Basically, it's like how many of the agents kind of collide among all the agents. The y-axis here is task completion. What do you mean? I mean by task completion is they can reach their destination sort of with a little bit of delay, because a lot of the, for example, some of the RL approach, one of them is like RL with shielding. It will always ask you to wait. And the most conservative way to be safe is just to wait. Each time you let one agent move, then you'll be very safe. But we don't want to have a lot of time delay because we want to do collision avoidance. So what we are measuring here is if the agent can reach their destination within a certain amount of time. We don't want this collision avoidance to add more than 20% of time delay. If they have more than 20%, we say they didn't accomplish their task. So here for our case is probably, I don't know as of now, but back to in 2 years ago, when we have this, it's the only work that can give you almost 100% for both, and others kind of have sacrificed one for another. And as I noticed some people notice it's not 100%, it's almost 100%. It's somewhere between 96% to 100%. And that's one limitation I want to bring up in advance. There are a couple of reasons it's not perfectly 100%. One is, of course, this is training, depending on the architecture you have selected, or depending on the training samples you have collected, it may not be the perfect one. And another reason is there are unconstructed uncertainties, disturbances that we didn't consider in training. So in training, we didn't give like a huge wind, but in testing, we actually give a pretty fast speed of the wind to see how well they can tolerate all these uncertainties. And you may also wonder, do we need more samples than RL? Luckily, we do not. We actually only use 10% of the training samples than RL, and we can get nearly perfect safety rate, while RL kind of struggles still around 50–60%. Some people may wonder, like I said, your model could be inaccurate. In our case, the model doesn't have to be accurate. The model can be learned. You can learn a model while collecting some data from the black box simulator. And we can also tolerate some sort of a model error. Model error in the sense, if there is up to 20% of like a relative model error to the actual model, you can still perform pretty well. And there's a little bit of detail here that I'm going to skip, but be happy to talk more if you're interested in knowing how to tolerate the model error in the training and still making sure we converge to a good barrier certificate for the actual system. Another work I'm really kind of proud of is not just a lot of drones, but a very realistic scenario on the F-16 model. This F-16 work is, this model is proposed by the AFRL, the Air Force Research Lab at US. And what they are trying to do is to create a, what they claim, the highest fidelity model of F-16. It's a Simulink model. It's like back to the old days of MATLAB Simulink. I don't know how many of you still work on Simulink. It's a nightmare. Like you have blocks and we open one, there are many more, and you open one, there are many more. You don't know what's the end. And one of them could be a lookup table. Another one is like some unknown filter. And another one is like a hidden there. You don't even know what's happening inside. Anyway, that's how this model looks like. I don't know how many of you have seen the latest Top Gun movie, but what they would really want to do is to learn a controller for this, construct a controller for this F-16 model so it can accomplish a bunch of tasks like what Tom Cruise is doing in Top Gun, like pulling up when you're getting close to the mountain, or follow these waypoints to travel through a corridor. That's basically what they want to do. And this Air Force Research Lab people that we work with, they construct their own controller based on their experts on flight control. And it worked kind of okay, but you can see it kept some sort of distance to the waypoint. And the reason they cannot push that exactly to the waypoint is because this aircraft will lose speed if you're doing too much. So this is like the way to fly it while still kind of follow some sort of waypoint. Of course, if we are like the pilot, we don't want to be able to not miss some waypoint. We may collide to some sort of mountain if we do that. And we have just tried the exact same thing that we have mentioned. I wouldn't say exact, almost the same thing, because now it's a super high dimensional system. It's 16-dimensional state space. Just like imagine that if you want to just sample in that state space, it should be a huge amount of data that we need. But it's almost a similar technology that we want to learn a controller as a neural network together with a control certificate. In this case, for waypoint tracking, it's just a Lyapunov function, and you can do whatever I said previously. Can do like a pull up from a surface when it's getting too close to a rock on the mountain or something, and we can our controller can track these waypoints perfectly without losing speed. And if I show you how the other machine learning based approach do, they actually do some interesting things to us. For example, PPO, and this is a imitation learning algorithm, they will let the aircraft spin like crazy. I'm sure you don't want to be like a person who is taking that one. I will throw up for sure. But this, we don't know why, but probably this is associated with reward hacking, because by spinning very fast, it's difficult to lose speed and crash. We have seen other reinforcement learning, imitation learning kind of approaches. Some of them can fly fine, but they cannot really reach the waypoints that we want to. Not to say that we only need 5% of the data needed by the other approaches. Another thing that we have tried, because I'm running a little bit behind, I will briefly mention is previously we studied these certificate functions for robots, where the robot is supposed to be safe. The robots, we have some information from physics and math about how that robot looks like. But how about human behavior models? So here, what we are trying to do is we're trying to use decentralized barrier certificate to capture the intention of human beings in a traffic scenario. Basically, when we are in a traffic scenario, whether we are like walking or riding a bike and driving a car, we kind of want to follow the traffic rule and also keep some safe distance to others, just like if we can. Of course, there are different kind of levels of aggressiveness here, but we try to grab that information from data and learn a data-driven model of how human beings react to the traffic scenario. So just now, I think you saw a biker was trying to get across a tiny subsection here before a roundabout, and now the setting is almost the same. This biker can observe the neighborhood using his eyes. But we actually insert this intention of collision avoidance using decentralized barrier certificate in this data-driven model that's learned from traffic data. What we have seen is it actually turns out this model can generalize to unseen scenarios in a reasonable way. Let me try to explain what we have here. So here we have learned how pedestrians react to a moving car. Now in the training data, when we constructed these models, we didn't have a car driving from right to left. It was a car somewhere else. Now we want to see if we have a car that these pedestrian models never saw before, what will happen? So here we have fixed trajectory. Fixed trajectory pretty much means the pedestrian will follow whatever they were doing, and imitation learning and our model. Let me try to show you like fixed trajectory, they will ignore there's a car there, so the car cannot really move. Imitation learning, I don't know, these people, they go like, they are crazy. They pretty much lost what they wanted to do when they saw like a new car here. You can see like this kind of behavior is ridiculous. For us, you kind of expect what can happen. They make a way if this car is slow enough and try still go to their destination while trying to make a way here. Similarly, there are different traffic scenarios. We can see how crazy these models can behave. Like this biker is like riding on top of a pedestrian, or at the roundabout, they pretty much lost what they want to go, where they want to go. But by inserting that barrier certificate, we can have much more reasonable behavior. Of course, this reasonable, by reasonable, I mean the intention of being on the road and also being able to like have some safe distance to each other. So here is how it looks like in all these different simulation environments that have promised. I'll be happy to play it for longer, but I also want to show you that the hardware, we put these learned controllers on hardware without training. Again, everything was trained in simulation. We have some sort of a very simple model that we use to train simulation and put in hardware. The first case here, you can see there's two robots are trying to push a box to a desired location. And it doesn't know how heavy this box is. It doesn't know the friction. It doesn't know the final pose of the desired location before it starts to push it. And there's also another person being very adversarial. I don't know whether you have seen it, but the other person is trying to use a stick to poke that box away from what the robot was trying to do. But this box is, they have actually pretty robustly pushed this box. This robot says can pretty robustly push the box there. We have tried this on a manipulator, just a barrier function for manipulator when it's having a load that exceeds its maximum control load. But we don't want to see some abrupt changes. So abrupt changes on the arm will harm the hardware. You can see barrier function, even it cannot really handle that lift anymore. It will be able to smoothly like drop. We also try this on hardware of a ground. These two are basically the same robots, but we are maliciously blocking the robots in whatever way you can throw a box to block its way with the barrier, with the certificate. Here we have both the barrier function and the Lyapunov function. Now you can see that guy can make a very smooth transition here to reach the goal. But if we use pure like SLAM-based planning, there is a way to block it and make it into a deadlock. So that's some sort of hardware demonstration. Of course, it's not as fancy as in simulation, but we're getting there. It'll be more if I'm going to present in front of you next year. I do notice that I know I'm running out of time, so I prepare certain questions that I'm often asked. I know some of you may have these questions. I will answer them in advance. So they are learned. Anything learned that is not trusted, right? It's learned from finite sample. How could we trust them? I have to say, during training, you can actually make the certificate function conditions hold everywhere by adding some assumptions. You have enough samples. The distance between the samples are close enough. There is some continuity assumption on the Lipschitz constant of the whole system. With all of that, you can actually prove that the certificate condition hold everywhere in the state space. Having said that, there's no free lunch. If we want to do that, it's going to face the curse of dimensionality for sure. We have been trying to use a couple of technology. For example, we are not sampling in the entire state space. We are only sampling in the reachable state. The reachable states in a high dimensional system is much smaller than the entire state space. That's why I said there's some trick there we can play to still learn a good certificate for a super high dimensional space. Some people may say, oh, your comparison with RL is not fair because you know the model information, RL doesn't. And my answer to that is that's true to some extent. And again, there's no free lunch. We cannot magically change a whole field by saying we can replace RL. We cannot. And the improvement in this case, improving both safety and performance, is really because we have embedded those control theoretical information in the training process. And not to say that our model can also be learned. So in that case, it's not that unfair, but we do have to use a slightly different procedure. Now, the difference is in RL, the policy is learned using reward as that guidance. For us, we use a certificate function as a guidance. And I know I will not be able to have time to reach here, but I'm also interested in higher level specification. In this case, these are manipulators. They are supposed to assemble something. Now, when doing this, we cannot just use collision avoidance because there are all dependencies. Sometimes the objects, you have to make them collide to make sure they clip, right? Like this Lego term. And all these arms, they also have to learn how to collaborate with each other. Also, still in this case, it's much easier to see. For example, I don't know whether you saw that, but if one arm wants to pull out the block on top of the others, the other arm have to hold it. Otherwise, you cannot pull two pieces apart. Another example, let me see whether it can play it here. This one here, you see that arm decide to hold. It's not because it's learned to be so. We actually have embedded the dependency that you have to wait for that bottom thing. Otherwise, you put the piece, it will just drop instead of staying there. So there are underlying logical dependencies and time dependencies between all these different components. Actually, those are higher level of, I call it safety object, but higher levels of requirements that we can kind of accomplish using similar approach that I have talked about. But here we have to use a different kind of certificate function to ensure all these logical dependencies are satisfied. So let me stop here, and by summarizing using one sentence, what we have shown, hopefully I can convince you that there is a way to combine the strength in control theory. I also put formal methods here because that's the thing for the higher complex requirement thing. I didn't really get there. But we can combine the rigor in these mathematically grounded approaches with the effectiveness in data-driven learning. And as a result, that can provide us safety assurance for the planning and control of quite challenging autonomous systems. So that's all I want to say. I have a QR code here that kind of have everything, the code that generates all the simulation environments I have talked about.
So thank you very much, Speaker, for the very nice presentation. And we're a little bit over time, but I think we have time for maybe one question or yeah, please.
Yeah, thank you for the talk. And for the barrier safety performance, I think you have assumed that you will conform to the satellite.
Yeah.
How likely the input is to satellite? It depends on which barrier function I pick. Right?
Which barrier function?
I mean, I can pick multiple barrier functions that have the same kind of safety.
So here, your barrier function is also learned. We are not picking a barrier. You're only defining what he means by safe and unsafe. And there could be many different barrier functions underlying there that can give you the same thing as long as their barrier kind of align with what you mean by safe and unsafe.
You take into consideration when you learn, the barrier function that shouldn't be too aggressive to your control input.
I would say that is possible if you can find a function, differentiable function that can define that as a safety property. If not, then that won't be able to be handled in this approach.